Thank you very much indeed. So let me add my thanks to everyone else's, to those who've worked so hard to organise this meeting, and also to express our thanks to Sir John Templeton, whose extraordinary combination of generosity and imagination makes all that we do in meetings like this possible. There's always a danger in a session like this that afterwards you hear people leaving the room muttering to themselves, saying, well, I'm still confused, but at a deeper level. Let's hope that we can do something to clarify things. And because I shall be presenting some actual results, I also want to acknowledge some of the people who've contributed in the lab to some of the work that I'm going to show you. Now, in the science and religion dialogue, science and religion have in common a shared passion for the truth. A common language is only possible to a limited extent for the simple reason that each discipline has vocabulary that is necessary for the concepts of that discipline. And to that extent, you just have to take the trouble to get your head round the concepts and acquire them. But nevertheless, there is this shared passion for the truth. One professor of English at Oxford, John Carey, put it like this: science's aims seem identical with those of theology in that they both seek to discover the truth. Science seeks the truth about the physical universe, theology about God. But these are not essentially distinct objectives, for theologians, or at any rate Christian theologians, believe God created the universe, so may be contacted through it. And as well as a shared passion for the truth, there is to a large extent a shared methodology in critical realism. And by that I mean there is a reality of the thing known that is something other than the knower, and the knowledge depends on a flow of information, if you like, a kind of dialogue between the known and the knower. This path leads to critical reflection on the products of our inquiry into reality, so that assertions about reality acknowledge their own provisionality. That was written by a theologian, but I think it would be shared by many scientists. And this is all very well until you get to the quantum realm. And you start to ask the question, does science in the quantum realm describe some objective reality, by which I mean that physical objects have definite properties and occupy... Is that all right? Was that a protest? No. That physical objects, I thought you disagreed or something, no, have definite properties and occupy definite states independently of whether they are observed. And that is consistent with our macroscopic experience, our us-sized lives, that definite events have definite outcomes. Trouble is, it doesn't work in quantum mechanics. And in quantum mechanics, all possibilities with a non-zero probability amplitude remain open. And this is a long-standing problem from the early days. It's epitomized in the dialogue between Bohr and Einstein. Bohr asked, what can one say? He, I think, would have said, oh, what's happened? Is that right? That macroscopic objects, I beg your pardon, microscopic objects like electrons and atoms and so on are simply not the kind of things that possess properties independently of the macroscopic apparatus used to observe them. So for Bohr, the reality was the outcome of an experiment. And you could not talk about reality independent of the apparatus that you were using to make the measurement. Einstein couldn't stomach that. And whereas Bohr was content simply to ask, what can one say, he wanted to know what is the case. He wrote in 1945, I incline to the opinion that the wave function does not completely describe what is real, but only to us an empirically accessible maximal knowledge regarding that which really exists. This is what I mean when I advance the view that quantum mechanics gives an incomplete description of the real state of affairs. And actually, 10 years before that, he'd published a paper. It's the famous Einstein-Podolsky-Rosen paradox. And the title of the paper was that quantum mechanics is incomplete. The experiment was so difficult to do that at the time it was just a thought experiment. It actually was only about 40 years later, after the development of some important mathematics, that the experiment could actually be done. And when it was done, it showed that at least in this respect, Einstein was wrong, and that what he had thought would prove that quantum mechanics was incomplete did not do so. Now, one of the recent areas of development in thinking about this long-standing problem is the question of statistical interpretations and the extent to which statistical interpretations are satisfactory. One of the most important developments, I think, in the last 10 years in quantum foundations is a theorem due to Pusey, Barrett, and Rudolph, where they've tried to examine the extent to which you can get over this problem by having some underlying physical states which underpin the quantum states that we've already seen are not amenable to this kind of realistic interpretation. So on the little sketch here, this axis lambda, this is a great simplification, but I hope that the cartoon is useful. This here is a way of describing all these different physical states. And you could have a picture where a quantum state, that's this one here, has some distribution of these underlying physical states, and another quantum state has a different distribution of underlying physical states. And if there's no overlap between those two, that's given the label of an ontic interpretation. It would be very attractive from some points of view if you could have a statistical interpretation where there was some overlap of these. And this is illustrated here. So now you see some of the physical states could, if you make a measurement, give an outcome of that quantum state, or the same physical state could, in another measurement, give that outcome there. And this would overcome the problem that you have in quantum mechanics, that you can prepare different states for which no single measurement will unfailingly distinguish them. And what the Pusey-Barrett-Rudolph theorem says is this. Take two assumptions. First of all, the system has a real physical state. You've got to have that because we're trying to get a realistic interpretation. And second, and this is a rather strong assumption, that independently prepared systems have independent physical states. If you accept that rather strong second assumption, then their theorem rules out this bottom picture here. So you cannot solve the problem with what is called this psi-epistemic interpretation. We have in my laboratory, funded by the John Templeton Foundation, a philosopher in residence. His name's Owen Moroney. And this year he's come up with a development of that theory, which in some ways is better and in some ways is worse. It's better in the sense that it does not need to make that assumption that independently prepared systems have independent physical states. It's less powerful in two respects, however. One is it makes extraordinary demands on the experimental precision that you need. That's illustrated by the diagram there. I won't go through it except to say that, we have done a proper mathematical analysis of this. And even in the least strong conclusion, you still need errors less than 0.5% in your apparatus, and that's quite hard in experiments of this kind. And even if you can get the errors way below that and go to a more complex system, technically a higher dimensional Hilbert space, the best you'll do is to rule out 50% of that overlap between the two functions in the cartoon that I showed you in the previous slide. These are conceptual developments which are just beginning to be experimentally tested. But what I want to do now is to change gears slightly, because I'm going to be tackling a different problem, but to show you an area in which experiments have actually now been done, which actually rule out certain philosophical interpretations. Now, I don't want to overstate the achievement. I don't want to stand up here and say that we've now solved the problem of reality, because it's a hard problem and it's got to be taken a step at a time. But science proceeds by tackling achievable objectives, and within the limited objectives of the experiments I'm going to show you, I think they are conclusive. A way of stating the problem is to go back to some work of Tony Leggett. Tony Leggett is a remarkable man whose first degree was in classics at Oxford, and only as a graduate did he learn quantum mechanics. He got good enough at it to win a Nobel Prize. And he has long worried about some of these issues. Under what he calls the quantum measurement problem, he says, look, you can classify reactions to this problem into three broad classes. The quantum measurement problem is what happens when you take a quantum system and measure it in a way that we can observe with our us-sized consciousness. One possibility is that quantum mechanics is the complete truth, and it does describe an external reality. The sort of theorems I was showing you in the last two slides are trying, and many philosophers of physics are doing this, trying to hold on to interpretation A. Interpretation B is that it's the complete truth, but it describes no external reality. Interpretation C is that quantum mechanics is not the complete truth about the world, and at some level between the atomic system at the bottom of the cryostat and our us-sized consciousness, some other non-quantum mechanical principles intervene. Now, of course, all of science is open to surprises and changes, and it may be that in the years to come we have a theory which is as different from quantum as quantum is from what went before. But quantum's been jolly thoroughly tested. And so Tony Leggett says, well, if you force me, I'll choose option B, but I don't like it very much. And he devised a mathematical inequality which would enable you to discriminate between different cases. So this is what's become known as the Leggett-Garg inequality, because Tony Leggett and Anupam Garg devised it in 1985. There at the bottom is the inequality for the mathematicians among you. But the key thing is that it is intended to prevent you from simultaneously holding two postulates. So a violation of that inequality means that you cannot simultaneously believe these two things. First of all, realism. And what that is if I have a two-level system, and it could be there or it could be there, at any given time it is in one of those two states. And the second postulate is non-invasive measurability. That is that it is in principle possible to observe the system without affecting its subsequent history. And that inequality, as I say, was first put forward over a quarter of a century ago. It proved to be so hard to test it experimentally that nearly 25 years passed before anybody tried. There have been various attempts. I can only say that Tony Leggett says that the one that I'm going to show you is the only one that really does it. Here, let me just fast forward to the results of the experiment. At the top there are the sort of pulse sequences that we used in the quantum system. We did it with phosphorus atoms in a very pure sample of silicon. And we tried to measure this inequality. And where is my little pointer? Here we are. Look at this first set of results here. The black curve is the predictions of quantum mechanics. The black spot there is the experimental result. And the grey one, for those of you who can see it just below it, is the experimental result corrected for known systematic errors in the experiment. Now, what are the other two curves? Well, what we want to show is that the experimental data lies below the bound permitted by classical realism. But when we came to analyze that, we realized, of course, that we were doing a real experiment with imperfect initialization. And the bits that were imperfect, you could say, well, they're going to be random, they're not quite right, but they'll cancel each other out. And that position would be adopted by the person we dubbed as the moderate realist. Here he is, MR. And the moderate realist would have a lower bound for his theory, given by this blue line here. And you can see that we've comfortably violated the Leggett-Garg inequality for the moderate realist. But then we thought, but what if there's a really aggressive realist? What one of this year's Nobel Prize winners calls the neurotic realist, the conspiratorialist, who says these ones that aren't perfectly initialized, maybe there's some unidentified law of physics that you don't know about that means that they all conspire to give you the worst case. And you can see that our experimental data would not have satisfied this aggressive realist. So then the person doing the experiment, Stephanie Simmons, said, well, I'm going to work a bit harder at this. She worked a bit harder, she polarized the spins a bit more, and she got this second lot of data here. And now you can see that even this aggressive neurotic realist would have to be satisfied that the Leggett-Garg inequality has been violated, and therefore he cannot simultaneously hold both of those postulates. Can we do better than that? Can we not only say that you can't hold both of those postulates simultaneously? You remember what they are. They're macroscopic realism and their non-invasive measurability. Can we do better than that and show that you can't even hold that first one, the macroscopic realism? And to do that, you need to go to a more complicated system. It has to be a three-level system. If you want to be technical, you have to move into three-dimensional Hilbert space. So in order to do that, we revived another experiment that had been postulated. As it happens, it had first been conceived the same year as the Leggett-Garg inequality, 1985, by a pair called Yakir Aharonov and Lev Weidman. And it later became known as the quantum three-box paradox. And the quantum three-box paradox is set up, if you like, as a game between two people. Bob is the classical macro-realist, and Alice, who is the younger and more intelligent of the pair, holds on to quantum theory. If classical macro-realism is correct, then Bob will win this game. If quantum theory is correct, then Alice will win it. And the game involves three boxes, or it's rather like, you know, the three-shell game, or three cups, where you have three cups on a table and one ball under them, and the guy operating it cons you out of your money whenever you bet on it. So we have three boxes, and Alice puts a ball in box number 3, and then when Bob's not looking, she shuffles them around so that it's completely random as to which of the three boxes that Bob looks at he sees the ball would be in. Alice then leaves the room. There's some impartial person there to ensure fair play, and Bob can open one of the first two boxes. He can open one or he can open two. And he can look inside and then shut the lid. If he does not see the ball, he wins, provided Alice subsequently accepts the game. And if you're used to these things in quantum theory, it's a pre- and post-selection experiment, which actually was conceived by thinking about time going in both directions in just the kind of way that Vlatko was talking about. Alice comes back into the room. She's allowed to shuffle the boxes around. She does not know which box Bob opened, except that it was one of the first two, nor does she know what Bob saw. She can then look in box that's now in position number 3. If she sees the ball, she accepts the game and accepts the bet. At the start, she'd given better than 50% odds. Now you can see how Bob is thinking. Bob, remember, is a classical realist, and he analyzes this and he says, well, at best, you know, Alice is going to be doing something like guessing when I tossed a coin, which way it came up. So if she gave 50-50 odds, you know, it'd be about fair. And she's giving me better than 50-50 odds, so I can't lose. I'm going to play this game. To his dismay, in the perfect case, he finds that Alice wins every time. Every time she post-selects the game, because she saw a ball in box 3, it turns out that, hey presto, he had seen a ball in box 1 or 2 and he loses. Now let me show you how we actually do it. We're going to use, we did use, a particular kind of defect in diamond that has 3 nuclear spin levels. Here they are, and these correspond to the 3 boxes. So we can put the defect into one of these 3 energy states, and that corresponds to the ball being in box 1, 2, or 3. To open the lid of the box, what we do is we apply a microwave pulse with a frequency corresponding to which one we want to look at. So, for example, if we wanted to look at box number 2, we'd apply a microwave pulse of frequency corresponding to this green arrow, and then we apply optical radiation and look for fluorescence. And if we succeeded in moving it to here, then it'll fluoresce, and that's the equivalent of seeing the ball in the box. And then to shut the lid, we apply another pulse that puts it back there, and actually we check that we've shut the box by looking for fluorescence again. So that's how we do the experiment, and it's a real experiment. There's the actual pulse sequences, and you don't need to go through them except to note in passing, what are we doing in this experiment? We're sending classical information in at this end here. We've got a quantum experiment that goes on in its quantum-y way, and then we get classical information coming out the other end. And if you really want to think how amazing this measurement problem is, that's what we're doing day in, day out in the lab, and we do not understand it. We really don't. Anyway, we can indeed.
Because you have now more than 20 minutes.
Okay, yeah, sure. So let me show you 2 slides of measurements and the conclusion slide, all right? So here are Bob's measurements. He wants to know whether Alice has cheated on the initialization, and he wants to know whether she's placed the ball randomly, and he wants to know if he looks a second time, does he get the same result? And here are the data. So he finds with equal probability that the ball could be in box 1 or box 2 or box 3, and it's 33% each, so when you add them all up, you get 1 ball, and it's randomly between the 3. Moreover, if he finds it, for example, in box 2 and repeats the measurement, he finds that it's in box 2 the next time. These are real experiments, so it doesn't go up to 100% because they're real data, but we know where those errors come from, we know how to account for them. And now Alice makes some observations, and the first thing we want to know is, do her observations depend on Bob's? Can she tell which box he looked in? And can she even tell whether he looked at all? And then we want to know whether she can win. Now this is a truly remarkable result. I'm going fast through it, but it's perhaps not surprising that she can't tell any difference between box 1 and 2 because there's a symmetry between those. But in a quantum experiment, you expect an observation to change things. And amazingly enough, she can't tell whether or not Bob has done a quantum measurement at all, whether he's looked in the box. Given that that's the case, it's then even more astonishing that she does indeed win. If it was a perfect experiment, she'd get it right 100% of the time. It's not perfect, it's a real experiment, but she's way above the threshold that a macro-realist could account for. And in fact, if you recast this as a Leggett-Garg test, you show, and everybody knows now from the CERN experiments what it means to have a certain sigma outside the bound. If it's a fair sampling assumption, she's exceeded the macro-realist inequality by 11.3 sigma, even if you take this aggressive realist, neurotic position, she's still achieved it by 7.8 sigma. Now, because we really have eliminated the possibility that the measurement is invasive, because it really is a non-invasive measurement in this experiment, we don't just say, well, you can't believe both of those simultaneously. We can actually say, you can't believe the realism. So this is a limited objective. I'm not saying it's answered the whole problem, but I hope you can begin to see that you're getting an experimental handle on some of these conceptual questions. So this is the conclusion slide. Question, been around for 80 years or more, are quantum states fact or knowledge? And we're now seeing rapid progress conceptually and theoretically in excluding certain interpretations. And the tools and the materials and the techniques are now becoming available to examine certain interpretations experimentally. So to throw this up to discussion, I was asked to give a couple of open questions at the end. Question number one is, if you accept that this is a way of using evidence to answer questions about reality, in what other fields of inquiry can progress be made in evidence-based reality? And question number two is this: how do open questions in quantum reality help in considering open questions in the science and religion dialogue? What I mean by that is this: that if someone who really didn't like the sort of science that I do attacked me, he could say, you're full of inconsistencies. You don't have a coherent picture of what happens when you make a measurement. And I have to accept that that's true, but also be passionate about continuing in the endeavor, partly just because the experiments and the theory do work, partly hoping I will make progress. And I wonder if there's some analogy to that in our science and religion dialogue.
Thank you very much for the two talks. So you please also come. And now we take questions.
You'll do the hard ones, and I'll
do
take
the
the
hard
easy
ones,
ones,
okay.
all right?
Yeah, please.
That's a, Michael Murray, that's a hard one. You can take it.
Well, sorry, Andrew, this one's for you. So I think what's there are two things that are bothering me. I'll tell you what both are, but I only want you to speak to the one. So I'm still not sure what the analog is supposed to be of the three boxes when we're looking at the particular physical setup you have in mind in the lab. I'm still having a hard time seeing what the analog is, but here's the question.
Yeah.
So you claim that there are these two inconsistent propositions, one that you've called realism and the one you've called non-invasive measurability.
Yes.
And I think I'm still not seeing why there's an inconsistency there. I suspect it boils down to what you mean by available states. So I think what you mean to say is that one of the available states can't be a superposition of a manifold of states. But why is that? Why does realism commit you to the idea that what's really out there is not that? Pre-measurement, that is, it just is a manifold of a superposition of states, and there's nothing unreal about that. That's just how it is. I guess if you hold that, then I don't see what the contradiction amounts to.
Well, I think it goes back to this slide here, so tell me if I'm addressing your question. It goes back to the thought that by reality, we mean that physical objects have definite properties and they occupy definite states independently of whether or not they're observed. And that is the kind of reality that I think that Tony Leggett was wanting to address in his Inequality. And if you accept that definition, and then you apply it to a two-level system, just to make it a simple model, then you do have to say, well, you know, if the outcome is determined by the properties of that system, then it's got to be in one or other of those states.
Yeah, I guess that's the claim I want to challenge. I mean, with no confidence at all, it's worth challenging. But the idea is that definite properties, why couldn't one say that the physical state has the following definite property? that it's a superposition of a manifold of states, and that is the definite property. That's just...
I think you are right, and that's probably close to what I believe in. So, I mean, this is exactly the multitude of interpretations of quantum mechanics. So I feel that I support claim A that Andrew wrote down. So I think, I'm happy with quantum physics being the final word on the whole picture. And I'm also happy calling myself a realist in the sense that you are describing. But I think Andrew is defining realism in a stricter sense that goes back to Einstein. And of course, I think some people would call this naive realism. And what you are talking about is real realism or whatever, something that's a bit more sophisticated. But I think most physicists would probably subscribe. I don't know if
I think
should
that's
speak
right.
for everyone, but I think...
So let me elaborate a little bit more on that. There are some statements of quantum theory that are fully realistic in the technical sense. The best known example is the de Broglie-Bohm theory, which is isomorphic with quantum mechanics, although it has a slightly different formulation, but it gives exactly the same predictions, and it is fully realistic in a way that I think would satisfy everybody. And John touched on it yesterday evening in his talk, and you cannot rule it out experimentally because it gives the same answers as quantum mechanics. So any experiment that is consistent with quantum mechanics will be consistent with the de Broglie-Bohm experiment. So in the end, you end up judging it on other criteria. Do you find it satisfying, beautiful, whatever your criterion is? There are other interpretations, or some people would say statements of quantum mechanics, which are fully realistic, of which the most celebrated one is the Everettian interpretation. And if you want to find a hotbed of people who are passionate Everettians, come to Oxford, because there are plenty of them there. And they will find that fully satisfactory, and they will say that is the only satisfactory understanding of quantum mechanics. And then there are other families which get round the measurement problem by actually introducing changes into the formulation of quantum mechanics. So they're sometimes called the continuous spontaneous localization theories, of which the most well-known one is the GRW theory. And those ones actually have additional terms in. Of course, there's a bit of Darwinian selection that's gone on because they're completely consistent with quantum mechanics in the regime where quantum mechanics has been tested, but they predict departures in realms that are outside any presently available experiments. But those ones in principle could be tested, and if you were clever enough at the experiments, you could see whether you could find a discrepancy that would be consistent with those and inconsistent with current statements of quantum theory.
Okay. More questions?
That's probably a longer answer than you wanted.
I have a question to Dr. Bidra about you were talking about quantum mechanics in order to describe a completely classical experiment.
Yes.
So I don't think it is really quantum mechanics. It's a mathematical formalism which resembles the formalism of quantum mechanics,
Yes.
but it's not the quantum mechanics as a law, a theory to describe the reality.
It's a very good point, and actually, believe it or not, there is a school of thought within quantum physics. It's one of the schools that Andrew has not mentioned yet. There are probably as many schools of thought as us physicists, if not more, right? Some people say there are more. And I think the idea is that this would be called idealism in my view, in the sense that it's all in your head. So basically, you have certain observations out there, but you have to sort them out in your head. And the question is, what is the most economical way of doing that? So this would say quantum mechanics is true, not necessarily because it's out there, but because that happens to be the way you are thinking about it, and that's what makes it efficient. And I think you can defend this picture. People in Vienna, for example, in the group of Anton Zeilinger are very close to this. They love this paper. I don't. It goes very much against my philosophy and my beliefs, and that's why I like it as well, in a sense, that it really goes counter to my intuition. But I think you're right. This doesn't say anything about nature. It only says about what is the best way of compressing knowledge regarding information. Yes? It's too late. Dinner.
Yeah. Last chance? Yeah, please. Good, thanks.
Just, would a reversible chemical reaction actually satisfy your conditions for time going backwards and forwards?
That's a good question. I think that you probably, the answer would be no, in the sense that the conditions with which you started are different. So when you go in one direction, the initial conditions are very different to the backwards direction, and what you have to do in order to make the reaction go in the other direction, if you like. I don't know if that makes sense. And I think, in fact, most of the irreversibility proofs that we have, which are called fudges in some sense, do take this approach, that they say, let's start with one initial condition in the forward direction, but when we reverse physics backwards, we start from a different state. And then you can start to see maybe differences between the forward and the backward flow. But if you really zoom in, and if you make all the details of this analysis absolutely identical, so that means your final state is exactly the final state you reached when you were going in the forward direction, and that's where you're going now backwards, then the laws of physics really tell you that there is absolutely no asymmetry between the two. So usually I think in chemistry and in more complicated processes, in biology and in macroscopic physics as well, what happens is that there is a distinction between past and future that's put in by hand. By hand means by someone who does the experiment. And I'm then reversing it in a different way, and in that sense I will get the distinction between the two. But if you really make all things equal, then somehow you will never get this irreversibility from the fundamental laws of physics. I'm not sure I'm actually answering what you asked. I feel a little bit dissatisfied, probably more than a little bit. But.
Okay.
To pick up on this. Yep. So in evolution we have irreversibility also in a certain sense, except that the asymmetry that you are talking about is not put in experimentally, but it comes by stochasticity, because some substates of the system, let's say a protein, are not controlled by natural selection, right?
Yes.
So which means when the evolutionary process went forward, there were some residues in the protein that were, mechanistically necessary to make the substitutions that make a functional difference adaptive. But afterwards, you basically burn your bridges, because these amino acids are not under the maintaining influence of natural selection anymore, so you lose them to entropy, which means you cannot, by reversing the originally positive substitutions, you don't get the same outcome as in the ancestor.
I think you are actually, it's a perfect example, and you are outlining more or less how Boltzmann, one of Boltzmann's derivations of what he called the H theorem, the increase in entropy, works. And what he did is he had systems interact with one another, but then what he ignored is the correlations that are created due to this interaction. So that's exactly the deletion of information that you mentioned. And once you do that, then you get the increase of entropy very, very naturally. But that's because you yourself, in a way, put it in there by making the assumption of the ignorance of correlations, if you like. And sometimes this is justified because nature does it for you, if you like. And then for all practical purposes, it really ends up being like that. But I think if you do retain all the information, then there is no... That's the point. Thank you.
You can just say a little bit about this in information processing, that most, or probably all current computers have a direction in time when they're doing their information processing. So, for example, if you have a NAND gate, you've got two inputs, one output, and you've then lost what the two inputs were. You don't have to do computing that way. You could do it reversibly. And in principle, there are possibilities for huge savings in energy. Because if you do computing reversibly, it can go forwards and backwards in time, and you never ever need to use any energy except in one case. And that's whenever you reset a bit. So if it's a binary bit, then you use kT log 2 is the minimum amount of energy that you need to use. And this actually is a sort of something that's conceptually important. It's also full of hope because present computers are so inefficient. And you probably know the analogy that if an airliner were as inefficient as your computer in the way that it uses its fuel, then on a full tank you'd get a couple of centimetres down the runway, you know. So there's scope for great improvement there if you move to this time-symmetric model of information processing.
Brooke, I'm just a little perplexed, Andrew, by your second open question.
Yep.
And I just wondered if you could tell us why you thought that was an appropriate question to raise, because superficially it would seem that we're really talking about two extremely different things. One, physical processes at the quantum level. The other, the meeting of minds. Because when we speak of the science-religion dialogue, that is shorthand. I mean, science itself doesn't dialogue with anything, and nor does religion. We're talking about human minds and the meeting of minds, which is so splendid on an occasion like this. But I just don't see really how you're even imagining that there might be some kind of analogy between those two cases.
Well, thanks very much, John, for that question. I wanted to start off by saying that both science and theology, I think, have a natural feeling that they want to work by critical realism, if you like, skeptical realism. And I talked a little bit about how science would like to be realistic. I would say that theology, at least Christian theology, which is what I know best, is strongly realistic. I think the New Testament is completely realistic. A couple of years ago, we had a conference to celebrate John's 80th birthday, and at least 3 of the speakers quoted the prologue of John's Gospel. In the beginning was the Word, and the Word was God, and the Word was with God. And I think John is thoroughly realistic in the technical sense, in the way that he writes, and you get it in the epistles, you know. I'm telling you about what we've seen and we've heard and we've touched it. You know, this is real stuff that we're talking about. Or in Hebrews, you know, you even get this sense that the spiritual realm is even more real than the material realm, which we encounter every day. They're about to make a film of C.S. Lewis's The Great Divorce. And the genius, or part of the genius of that book, is the way that he makes heaven more real than hell. The grass has a higher modulus of elasticity to show you how much more real it is. So I think that in the theology, we're talking about things that are real. But I accept that in my theology, there are some very important foundational questions that affect everyday life to which I do not have satisfactory answers. I do not have a satisfactory answer to how to describe divine action in a world that we're used to describing by the physical and natural sciences. I don't have a satisfactory answer to that, and yet I go on living the Christian life. And a critic could accuse me of being intellectually inconsistent. And I take comfort from the fact that I have comparable inconsistencies in my laboratory life. There are questions that are too hard for me, to which I don't have satisfactory answers, but nevertheless I still feel that I can go on doing it, not in a lazy way, not saying these questions don't matter, but saying that I can get on with things while at the same time I'm worrying away at those questions.
Any more questions? I don't see any, so thanks.